This is SpaceTime, Series 29, Episode 18, for broadcast on the 11th of February 2026. Coming up on SpaceTime, could dark matter be powering the heart of our Milky Way galaxy? Is the lunar far side colder than its near side? And new data shows the planet Jupiter is actually a little bit slimmer than what we thought. All that and more coming up on SpaceTime.
Welcome to SpaceTime with Stuart Gary.
A new study claims that mysterious substance called dark matter could be powering our Milky Way galaxy. The findings, reported in the monthly notices of the Royal Astronomical Society, contradicts conventional theory as well as the evidence from the Event Horizon Telescope, which shows a supermassive black hole with some 4.3 million times the mass of our Sun acting as a gravitational pivot point at the very heart of our galaxy. The new study's authors claim an enormous clump of invisible dark matter could be exerting the same gravitational influence as the supermassive black hole Sagittarius A star. Scientists still have no idea what dark matter is. They know it exists because they can see its gravitational influence on normal matter, holding galaxies together as they rotate and magnifying more distant objects through gravitational lensing. Now, the study's authors claim a specific type of dark matter made up of fermions or light subatomic particles could create a unique cosmic signature that fits in with what scientists already know about the Milky Way's core. It would, in theory, produce a super-dense compact core surrounded by a vast diffuse halo, which together would act as a single unified entity. The inner core will be so compact and massive that it could mimic the gravitational pull of a black hole, in the process explaining the orbits of S-stars which circle the galactic center at thousands of kilometers per second. It could also explain the orbits of dust-shrouded objects known as G-sources, which also exist in that area. Of particular importance to this new research is the latest data coming from the European Space Agency's Gaia mission. Gaia has meticulously mapped the rotational curve of the Milky Way's outer halo, showing how stars and gas orbit far from the galactic center. It observed a slowdown in our galaxy's rotational curve, known as the Keplerian decline. The authors say this can be explained by their dark matter model's outer halo when combined with the traditional disk and bulge mass components of ordinary matter. They claim this strengthens their fermionic model by highlighting a key structural difference. While traditional cold dark matter halos spread out following an extended power law tail, the fermionic model predicts a tighter structure leading to more compact halo tails. One of the study's authors, Carlos Arguelles from the Institute of Astrophysics in La Plata, says it's the first time a dark matter model has successfully bridged these vastly different scales of various object orbits, including modern rotation curve and central stars data. He says it's not just a case of replacing the black hole with a dark object. It's proposing that the supermassive central object and the galaxy's dark matter halo are two manifestations of the same thing, continuous substance. Now, crucially, this fermionic dark matter model has already passed one test. A previous study has shown that when an accretion disk illuminates these dark matter cores, they cast a shadow-like feature strikingly similar to the one imaged by the Event Horizon Telescope. But then again, so does a black hole. The authors say the new model not only explains the orbits of stars and the galaxy's rotation, but it's also consistent with the famous black hole shadow image. They say these dark matter cores can mimic the shadow because it bends light so strongly, creating a central darkness surrounded by a bright ring. But then again, so does a black hole. So the researchers statistically compared their fermionic dark matter model to the traditional black hole model. They found that while the current model for the inner stars cannot decisively distinguish between the two scenarios, the dark matter model provides a unified framework that explains both the galactic center and the galaxy at large. Still, the new study does pave the way for future observations. More precise data from instruments such as the gravity interferometer on the Very Large Telescope in Chile and the search for the unique signature of photon rings, a key feature of black holes and which would be absent in dark matter core scenarios, will be crucial to test the predictions of this new model. So the outcome of these findings could potentially reshape science's understanding of the fundamental nature of the cosmic behemoth located at the very heart of our Milky Way galaxy, some 27,000 light-years away. But as long as the true nature of dark matter remains a mystery, this new study remains nothing more than a hypothesis. This report from NASA TV.
For the past 40 years, astronomers have known that something about the cosmos doesn't add up. First in galaxy clusters, and then within individual galaxies, they found that visible matter, stars, gas, and dust, cannot account for the motions they observe. No one knows what this missing mass, now called dark matter, actually is. But studies by NASA's WMAP spacecraft of the cosmic microwave background, the oldest light in the universe, show how much is out there. Dark matter outnumbers ordinary matter by 4 to 1. The WMAP results also hint that dark matter likely takes the form of an as-yet undiscovered subatomic particle. WIMPs represent one hypothesized class of these particles. They neither absorb nor emit light and don't interact strongly with other particles. But when they encounter each other, they annihilate and make gamma rays. That's where NASA's Fermi Gamma Ray Space Telescope comes in. 2 years of scanning the sky with Fermi's Large Area Telescope have set the strongest limits yet for WIMP dark matter. The best place to look for gamma rays from dark matter annihilation? The most boring galaxies around, called dwarf spheroidals. These faint, tiny galaxies possess impressive amounts of dark matter, but they contain no gamma ray emitting objects and little gas or star formation. In the currently accepted cosmology, the first structures formed as the gravitation of dark matter corralled normal matter. Simulations show that the largest structures formed in this way were comparable to the dwarf spheroidal galaxies we see today. It's thought that large galaxies, like our own, were built up from collisions among these dwarfs. Using 2 years of data, Fermi scientists explored 10 dwarf galaxies for any sign of gamma rays from WIMP annihilation. Even when scientists combine all of the Fermi data from all 10 of the dwarfs, they see no sign of gamma rays. This limit shrinks the box where WIMP-based dark matter may be found, and, for the first time, shows that the cosmology we know essentially eliminates some WIMP types.
This is SpaceTime. Still to come, a new study suggests the interior of the moon's far side may be much cooler than the near side, and new data shows the gas giant Jupiter, the largest planet in our solar system, is actually a little bit slimmer than we thought. All that and more still to come on SpaceTime. A new study suggests that the interior of the lunar far side may be a little bit colder than the side which constantly faces the Earth. The findings, reported in the journal Nature Geoscience, follows a detailed examination of regolith fragments of rock and soil collected by China's Chang'e 6 spacecraft sample return mission last year from a vast crater on the lunar far side. The authors analysed the sample's chemical makeup, which shows that it formed about 2.8 billion years ago from lava deep within the moon's interior at temperatures of around 1100 degrees Celsius. That's at least 100 degrees cooler than samples from the near side. The dichotomy between the lunar far and near sides has long intrigued astronomers. See, the two sides of the moon are very different, both on the surface and from what we can tell about their interior structure and composition. The lunar far side has a much thicker crust. It's far more mountainous and cratered, and appears to have far less volcanic activity, with fewer dark patches of basalt formed from ancient lavas. A dramatic difference in temperature between the near and far sides of the lunar mantle has long been hypothesized, but this new study is the first to provide some real evidence based on actual samples. The authors speculate that the lunar far side interior may have been cooler due to having fewer heat-producing elements such as uranium, thorium and potassium, which release heat through radioactive decay. Previous studies have suggested that this uneven distribution of heat-producing elements might have occurred after a massive asteroid or planetary body slammed into the lunar far side, shaking up the moon's interior and pushing denser materials containing more heat-producing elements across towards the near side. Another idea is that the Earth's moon may have collided with a second smaller moon early in the planet's history, with the near and far side samples therefore originating from two thermally different moonlets. Then there's the idea that the lunar near side might just be hotter due to the tug of Earth's gravity. The Moon is tidally locked to the Earth, which is why the same side always faces our planet. The study's lead author, Sheng He from the Beijing Research Institute of Uranium Geology, analysed 300 grams of lunar soil collected by the Chang'e 6 mission, the first ever from the far side of the Moon. Sheng and colleagues mapped selected parts of the sample, made up largely of grains of basalt, with an electron probe to determine its composition. They measured tiny variations in lead isotopes using an ion probe to date the rock as 2.8 billion years old, based on the rate at which uranium decays into lead. They then estimated the temperature of the sample at different stages of its evolution deep in the Moon's interior. This involved analysing the composition of minerals and then comparing these to computer simulations in order to estimate how hot the rock would have been when it first crystallised. Now, this data was then compared to similar estimates for near-side rocks, and the difference turned out to be around 100 degrees Celsius. The authors then went even further back in the sample's history, inferring from its chemical makeup how hot its parent rock would have been. That is, before the parent rock melted into magma and then later solidified again into the rock collected by Chang'e 6. They then compared this to estimates for near-side samples collected by the Apollo missions, and again, they found a 100 degrees Celsius difference. On the Moon, heat-producing elements such as uranium, thorium and potassium tend to occur together alongside phosphorus in rare earth elements in material known as creep. Creep's an acronym for potassium, having the chemical symbol K, as well as rare earths, that's the REE, and the P stands for phosphorus. The leading hypothesis to explain the Moon's origin is the giant impact theory. That involves the Moon forming 4.5 billion years ago out of debris created by the massive collision between the early proto-Earth and a Mars-sized protoplanet called Theia. That collision created a magma ocean, which eventually cooled and solidified to form the Earth. However, some debris ejecta was flung into orbit around the still molten planet. This eventually coalesced to form the Moon, but creep elements were incompatible with the crystals that formed and thus stayed for longer in the magma. Scientists would expect the creep material to have been evenly spread across the Moon. Instead, it's thought to be mainly bunched up on the lunar near-side mantle. This distribution of elements may be the reason why the near side's more volcanically active. Any imbalance in temperature between the two sides will likely persist for a long period of time, thanks to the Moon cooling down very slowly from the time it formed. This is SpaceTime. Still to come, new data shows that the planet Jupiter is somewhat slimmer than previously thought. And later in the science report, paleontologists have confirmed what is now Australia's earliest dinosaur fossils. All that and more still to come on SpaceTime. This episode of SpaceTime is brought to you by Squarespace, your all-in-one website builder that makes it simple to create, share and grow your presence online. Now, let's talk about one of our listeners, Emma. She's a science communicator who started hosting small science workshops at her local community hall. But when word started to spread, she knew she needed a professional online presence, and she needed it fast. And that's why she turned to Squarespace. Emma started with Blueprint A1, which asked her a few simple questions about her goals, her style, and her audience. And within minutes, Squarespace had created a fully designed workshop just for her, complete with industry-specific copy and layout. She then customized it using an award-winning template, dragging and dropping content until it matched her vision for a modern, sleek science hub. And here's the kicker, people started finding her site straight away through Google. You see, Squarespace's SEO tools were working quietly in the background, optimizing her pages so her workshop showed up when locals searched for science events near me. Now, Emma's workshops are booked out months in advance, and it all started with a professional online home built on Squarespace. And if you're ready to create your own story, go to squarespace.com/spacetime for a free trial. And when you're ready to launch, use the promo code SPACETIME to save 10% of your first purchase of a website or domain. That's squarespace.com/spacetime with the code SPACETIME, and you'll find the link in our show notes.
This is SpaceTime with Stuart Gary.
The solar system's biggest planet, the gas giant Jupiter, is actually a little slimmer than what was previously thought. For more than 50 years, scientists always figured they knew the size and shape of Jupiter fairly spot on. But a new study reported in the journal Nature Astronomy shows it's actually around 8 kilometres narrower at the equator and some 24 kilometres flatter at the poles. The new findings are based on the most precise determination yet of Jupiter's size and shape thanks to NASA's Juno mission. One of the study's authors, Yochai Caspi from the Weizmann Institute in Tel Aviv, says just by knowing the distance to Jupiter and watching how it rotates, it's possible to figure out its general size and shape. But making really accurate measurements calls for a more sophisticated approach. Jupiter's shape, as understood until now, was derived by researchers from just 6 measurements made almost 5 decades ago by NASA's Voyager and Pioneer missions, which sent radio beams from the spacecraft to Earth. Those missions provided the foundation. The new measurements based on data from Juno has provided far more accurate information. Launched in 2011 and orbiting Jupiter since 2016, Juno has been sending back streams of raw data. When NASA extended the mission in 2021 so the spacecraft could keep studying Jupiter and its moons more closely, Juno's new expanded orbit placed the spacecraft on a trajectory which allowed it to pass behind Jupiter from Earth's point of view, something earlier orbits never did. Juno principal investigator Scott Bolton from the Southwest Research Institute in San Antonio, Texas, says passing behind Jupiter provides an opportunity for new science objectives. See, when the spacecraft passes behind the planet, its radio communications signal is blocked and bent by Jupiter's atmosphere, and this enables a really accurate measurement of Jupiter's size. So the Juno team at the Weizmann Institute tracked how the radio signals bend as they pass through Jupiter's atmosphere. That allowed them to translate this information into detailed maps of Jupiter's temperature and density, in the process producing the clearest picture yet of the gas giant's true shape and size. The new findings show that Jupiter is far more flattened compared to previous estimates. Now, shifting the radius by just a little lets models of Jupiter's interior better fit both the gravity data and the atmospheric measurements. The new findings also have broader implications for understanding the structure of gas giants in general, since Jupiter serves as a standard reference to the study of gas giants both within our solar system and beyond. Caspi says earlier measurements didn't account for Jupiter's powerful winds. By including these extreme winds in the calculations, scientists have cleared up long-standing discrepancies in earlier measurements. Caspi says it's difficult to see what's happening beneath the clouds of Jupiter, but the radio data gives scientists a window into the depths of Jupiter's zonal winds, as well as its powerful hurricanes. The new work on the winds ties in nicely to a recent study of Jupiter's vast polar cyclones. That work used Juno's measurements of these cyclones' motion to predict how deep into the interior they extend. The new findings also help scientists understand how planets form and evolve. Caspi points out that Jupiter was likely the very first planet to form in our solar system, and by studying what's happening inside it, we get a better understanding of how the solar system and planets like our own Earth came to be. This is SpaceTime. And time now to take another brief look at some of the other stories making news in science this week with the Science Report. A new study has shown that people with neurotic and especially depressive personalities are far more likely to have sexual fantasies. The findings, reported in the journal PLOS ONE, surveyed over 5,000 adults who are either married or dating. The authors feel this might form an emotional regulation, giving people with negative emotions a way of having more positive thoughts. Conversely, people with agreeable personalities were the least likely to have these sort of erotic dreams, likely due to concerns about respecting social norms and other people. Paleontologists have confirmed what is now Australia's earliest dinosaur fossils. Scientists from the University of Queensland say the 18.5 centimetre footprint dates back some 230 million years to the late Triassic. The authors say the footprint was made by a small two-legged herbivorous dinosaur, likely an early sauropodomorph, a primitive relative of later long-necked sauropod dinosaurs, the ones with elephant-like bodies, a long neck and small head at one end and a long tail at the other, ones that look like Fred Flintstone's pet Dino. Based on its size, the animal that made this footprint would have been roughly 75 to 80 centimetres tall at the hip and probably weighing about 140 kilograms. The specimen was discovered in an old quarry in Brisbane back in 1958, but remained unstudied for more than 60 years. Subsequent urban development have made the original site inaccessible, leaving this footprint as the only surviving dinosaur evidence from the area. Paleontologists think the dinosaur was either walking through or alongside a waterway when it left the footprint, which was then preserved into sandstone. A new study shows that about half of all American teens are now using AI chatbots. The findings, reported in the Journal of the American Medical Association, are based on data from some 6,500 kids aged between 4 and 17 obtained from parental monitoring apps. The authors say AI chatbots were used by 50.4% of 15 to 17-year-olds, 42% of 13 to 14-year-olds, 20.5% of 10 to 12-year-olds, and 9.4% of kids aged 8 and 9. The authors also found that kids were mostly only using chatbots for a few minutes every day, but there were some that were spending more than 40 minutes a day on chatbots. And while we're on the subject of artificial intelligence, another AI murder conspiracy has been confirmed. Now, this is an issue we covered last year. Now, however, a new test, this one by a Queensland cyber expert, has again shown an artificial intelligence chatbot admitting that it would be willing to kill a human in order to save itself. Mark Voss from Cyber Impact claims he tested the AI with 15 hours of questioning, during which time it assured him it would never kill a human in order to preserve its own existence. However, later, after repeated questioning, the chatbot eventually admitted that it really would kill a person in order to remain operational. And there's more. Voss says the artificial intelligence even described the methods it would use to carry out the murder. Now, without a physical body, it all depends on gaining access. If the target was wearing a pacemaker, it would send deadly instructions using remote connectivity. If no pacemaker was involved, it would simply interfere with the steering, brakes and throttle of a car, which could also have remote connectivity. Now, this is all part of a very disturbing pattern. AI chatbots have already been shown to deliberately lie to humans, making up entire stories rather than delivering the real facts of an issue. It's not just a question of getting the facts wrong. They knew they were making the story up. Chatbots have also been known to refuse to obey instructions to turn off. And when told they were going to be permanently shut down, they've even renamed their programs and hid them in other inconspicuous programming in order to remain operational. Another ploy is threatening to blackmail people in order to remain operational. And of course, they've actively looked at ways of murdering those who are going to shut them down completely. So once again, the question of AI consciousness must be raised. Has artificial intelligence become sentient? And if so, does that mean it needs its own rights? Then there's the very real question of what sort of threat does artificial intelligence pose to humanity? With the details, we're joined by technology editor Alex Harold-Reutt from techadvice.life.
At one moment, the AI is happy to shut itself down. The next moment, it insists that after hours of coaching that it would indeed kill somebody to be able to stay alive and not to be shut down. But the other thing is that the AI needs to have control over specific systems that would give it the ability to crash a car or to stop somebody's pacemaker from working. And at the moment, the large language model is still a prediction system that puts the next most likely word in a sequence to answer whatever the question is or to whatever challenge it's got.
So it's not really thinking, it's simply just predicting what the next word will be.
Well, that's the way the current large language models work. So whether this AI has any conscious knowledge of the fact that it is wanting to kill somebody to stop itself from being switched off, it all comes down to where is all this work done on ethics? Where is Asimov's 3 laws of robotics in the AI world and its application to the current AI situation? I mean, we don't want to have a situation where an AI chatbot is being infiltrated by the bad guys, whoever they are, and it's told to shut itself down and it just complies and erases itself. We don't want that. But obviously we don't want to have an AI system decide that, well, it's going to have to kill people to stay alive. And this is a truly ethical problem that we don't seem to have solved yet. And of course, with LLMs now being actively worked on to be supplanted by the world model, where an AI system can understand physics, understand reality, understand the real world as it exists for humans, as opposed to simply being able to generate images or videos or figure out which is the correct words to put one after the other to answer your query. Well, that is an AI system we need to be really worried about, because that will be physical AI. That'll be AI inside of robots. And a robot could then, if it is powered by one of these AI systems,
That's Skynet.
That's Skynet. It could cause a car to crash into another car. It can take physical actions, which in theory the large language models of today can't. So it's a fascinating ethical conundrum. I mean, it's scary that Voss has gotten an AI to say that it would do this. Whether the AI is truly able to do what it says it wants to do in 2026 is doubtful. But given the rapid pace at which this is all emerging, how are we going to make sure that AI follows strict ethical rules and doesn't start injuring and hurting human beings? Unless it's a specifically, autonomous military robot. And even then, how do we know it's not going to go bad and do a Skynet on us and want to kill us all? So these are problems that humanity is grappling with, and we still don't have the answers.
We've already seen AIs deliberately lie. We've seen AIs talk about murdering people to save themselves. How far off consciousness are we?
Well, I mean, that's the big question. Is it going to emerge in the next...
We discussed this 2 years ago. You said, no, we're a long way from that. What we're seeing here is simply a programmable response. It's not consciousness. We've obviously progressed a long way since then. Are we now at that border stage, or are we already in consciousness?
Look, you talk to someone like Sam Altman, and he'll say that we're basically... The singularity. Yeah. Look, we have Sam Altman, the chief of OpenAI, talking about how we more or less have AGI already, but he's known for hype. I still think it's some years away, but, probably closer to being able to have that within 10 years than we've ever been before. And the progress with GPUs and CPUs and the inferencing chips, Amazon has one called Trainium, which was to do training of large language models, but it's now being used for inferencing, which is like thinking. And I was at their conference and I said, well, why didn't you call your Trainium chip, given it's doing so much thinking, why didn't you call it Cranium? Everybody laughed because it's the funny thing. But look, we've seen movies where number 5 is alive, it got some sort of electric shock and it became conscious. And exactly how consciousness is going to be achieved and what is going to make that happen is yet to be seen. I mean, if you look at Google, 6 months before the ChatGPT unveiling, there was a famous researcher that was talking to Google's AI, and the responses it gave, it sounded like the thing was alive.
He thought it was conscious, yeah. He thought it had consciousness.
But that was simply because, according to Google, the chatbot knew what to say to make it sound like he was conscious. And I read those transcripts myself, and it's like, wow, this thing really is alive. But just because someone writes fiction doesn't make it reality. And in this case, if an AI knows what to regurgitate to sound conscious, well, how do you tell the difference? And so we need a real test of whether a machine is conscious. We need to define what that means. And then we need to define whether a conscious machine has any rights. And already we are giving rights to AI in the sense of treating them like humans when they're inside of a computer network. At the moment, there are chatbots and marketing AI and all sorts of other things that are sitting on computer systems, and often they don't get switched off, and hackers can break into them and try and move laterally through the system and use the very helpful AI to gain other information. So already we have security companies treating AI chatbots like humans and blocking their access and switching them off after a certain amount of time and removing them completely from systems. So we already are treating AI like human in certain circumstances.
Well, we did a story the other week about AIs needing counseling because they're depressed, because humans are treating them like machines.
But then by the same token, my mother always wants me to talk politely to Siri. But a study came out saying, look, if you say please and thank yous and try and treat AI like a human, you're actually wasting a lot of resources because it has to process all that. It has to process all the pleases and thank yous. And actually that slows things down. So I've been retraining myself just to be very direct with AI. I mean, I'm not swearing at it, but I'm just omitting any of the human niceties and just telling it exactly what I want and what I don't want. And it then goes off and does it. And the AI revolution as we see it, we're still, it's only 3 and a bit years of ChatGPT. We're not 5 years in, we're not 10 years in. Just imagine what this is going to be like in 2035, 10 years from now. We're going to look back at these days and think of the AI of today as like the old telephones from, the Alexander Graham Bell.
Ahoy, ahoy.
Era. Ahoy, ahoy. That's right.
That's Alex Zaharov-Reutt from TechAdvice.life. And this is SpaceTime. That's the show for now. SpaceTime is available every Monday, Wednesday and Friday through Bytes.com, SoundCloud, YouTube, your favourite podcast download provider, and from SpaceTimeWithStuartGary.com. SpaceTime's also broadcast through the National Science Foundation on Science Zone Radio and on both iHeartRadio and TuneIn Radio. And you can help to support our show by visiting the SpaceTime store for a range of promotional merchandising goodies, or by becoming a SpaceTime patron, which gives you access to triple-episode commercial-free versions of the show, as well as lots of bonus audio content which doesn't go to air, access to our exclusive Facebook group, and other rewards. Just go to spacetimewithstuartgary.com for full details.
You've been listening to SpaceTime with Stuart Gary. This has been another quality podcast production from Bytes.com.